A Bloom filter is a data structure with many practical applications. It can be found in network routers, databases, and web browsers, just to name a few. We mentioned it in one of our recent videos when we discussed NoSQL. What are Bloom filters? Where are they used? Let's take a closer look. A Bloom filter is a space-efficient probabilistic data structure. It's been around for 50 years. It is used to answer the question, is this element in the set? A Bloom filter would answer with either a firm no or a probably yes. In other words, false positives are possible. That is, the element is not there, but the Bloom filter says it is, while false negatives are not possible. That is, the element is there, but the Bloom filter says it's not. The probably yes part is what makes a Bloom filter probabilistic. As with many things in software engineering, this is a trade-off. The trade-off here is this. In exchange for providing sometimes incorrect false positive answer, a Bloom filter consumes a lot less memory than a data structure like a hash table that would provide a perfect answer all the time. If a use case can tolerate some false positives, but not any false negatives, a Bloom filter could be very useful. And another key point though, we cannot remove an item from a Bloom filter. It never forgets. Now let's see how it is used. Many NoSQL databases use Bloom filters to reduce the disk reads for keys that don't exist. With an LSM tree-based database, searching for a key that doesn't exist requires looking through many files and is very costly. If you would like to learn more about how the LSM tree works, check out this video in the description below. Content delivery networks like Akamai use Bloom filter to prevent caching one-hit wonders. These are web pages that are only requested once. According to Akamai, 75% of the pages are one-hit wonders. Using a Bloom filter to track all the URLs seen and only caching a page on the second request, it significantly reduces the caching workload and increases the caching hit rate. Web browsers like Chrome used to use a Bloom filter to identify malicious URLs. Any URL was first checked against a Bloom filter. It only performed a more expensive full check of the URL if the Bloom filter returned a probably yes answer. This is no longer used, however, as the number of malicious URLs grows to the millions, and a more efficient but complicated solution is needed. Similarly, some password validators use Bloom filter to prevent users from using weak passwords. Sometimes a strong password will be a victim of a false positive, but in this case, they could just ask the users to come up with another password. These are just some well-known examples. There are many more applications of the Bloom filter. Now let's discuss how a Bloom filter works. A critical ingredient to a good Bloom filter is some good hash functions. These hash functions should be fast, and they should produce outputs that are evenly and randomly distributed. Collisions are okay as long as they are rare. A Bloom filter is a large set of buckets, with each bucket containing a single bit, and they all start with a 0. Let's imagine we want to keep track of the food I like. For this example, we'll use a Bloom filter with 10 buckets labeled from 0 to 9, and we would use 3 hash functions. Let's start by putting ribeye into the Bloom filter. The 3 hash functions return the numbers 1, 3, and 4. These will set the buckets at those locations to 1. Now this can be done in constant time. Next, let's put potato into the Bloom filter. The hashing function returned the numbers 0, 4, and 8 this time. Let's set those bits. Now, do I like ribeye? Well, we can ask the Bloom filter. Since the same input always hashes to the same output, ribeye still hashes to the number 1, 3, and 4. We check all those buckets, and they're all set to 1. So the Bloom filter says, I like ribeye, and in this case, it is true. Now let's see if the Bloom filter thinks I like pork chop. In this case, the hash functions return the buckets 0, 5, and 8. And even though buckets 0 and 8 are set to 1, bucket 5 is 0. In this case, the Bloom filter can confidently say, no, I don't like pork chop. But how do we get the Bloom filter to tell us something is there when it's not? Let's walk through an example. Let's say lemon hashes to the bucket 1, 4, and 8. Since all those buckets are set to 1, even though I don't like lemon, the bloom filter will return yes in this case, which is a false positive. In real-life applications, the size of the bloom filter is much larger than the example here. We can control how often we see false positives by choosing the correct size for the bloom filter based on the expected number of entries in it. These are trade-offs between space used and accuracy. If you would like to learn more about system design, check out our books and weekly newsletter. Please subscribe if you learned something new. Thank you so much, and we'll see you next time.